Welcome to cryptography session. Today I am going to give an explanation for finite fields and a few problems in finite field concept. So a finite field is one of the subdivision of field. So if you take field, field is denoted with F. So F is equal to Zn with two binary operations. So the properties of the basic five properties are satisfied with the second operator, and we should also satisfy the commutative property and inverse for both additive inverse and multiplicative inverse. So in addition with that, we should also satisfy the distributive property with these two operators. So if all these properties are satisfied, that field is that ring is called as commutative ring. So all commutative ring are considered as field. So if you take finite field, the meaning of finite means a countable number of elements. So it can be shown that the order of finite field, that means the number of elements which is available in a finite field. So the number of elements should be written only in the prime factors. So here P is denoted as a prime number and N means the factors are powers of those prime number. So the values which is available in finite fields are only in the format of P to the power N. So in this way we can able to find out the finite field notations, and these finite fields are used for defining the arithmetic notations over polynomial equations. For this concept only finite fields are used. And finite fields are sometimes called as Galois field. So it is denoted as GF. So Galois fields are defined for two values. One is for prime or prime factors, or we can able to denote it with 2 power n values. That means the powers of 2 value. For this set of values only, the Galois fields are available. So if you take GF of P, the set of integers are from 0 to P minus 1. So all these values are retrieved with the arithmetic operations modulo prime value. In this way only we can able to retrieve these values. For example, how can you find GF of 7? So if you want to find a Galois field, we should do two basic operations because it is a finite field. Finite field contains the basic operations are plus and cross. So here 7 is a prime number. So P is equal to 7. So then the value should be retrieved as 0, 1, 2. That means 0 to P minus 1. So totally 7 values should be retrieved with the help of both addition and multiplication operation. And then we should find out the inverse values, both additive inverse and multiplicative inverse of 7. So for these retrieved values, I draw a tabularized form. For addition operation, there is a need of retrieving these 7 values. So these are all Z7 values. So I write it in column and row order. And the answers are prime modulo 7. That means here 7 is the prime number. So if you add a 0 with any other number, the same number is available. So first row and first column values are same as this answer. So 1 plus 1 2, 1 plus 2 3, 1 plus 3 4, 1 plus 4 5, 1 plus 5 6. 1 plus 6 is 7, but 7 is not in Z7. So you should do modulus operation. So 7 mod 7 is 0. So in this way we can able to retrieve all the values within this table. So if you take all the elements in this particular table, the answers are only from the given set. So this is an addition operation. The same thing that should be done for multiplication operation. So if you do multiplication operation for 0 with any value, the answers are 0. So the first row and first column contains 0. 1 with any other number, the same number is occurred. So the same column value is there. For example, 2 3s are 6. 2 4s are 8, but 8 is not a number in Z7. So 8 mod 7 is 1. 2 5s are 10, 10 mod 7 is 3. 2 6 are 12, 12 mod 7 is 5. So in this way we can able to retrieve this table. This table also contain the values which are all same as the elements which is available in this set. So this is a multiplication operation. So we completed the addition and multiplication operations by using all the elements of Z7. The answers are only retrieved from the same set. And here it is an additive inverse. So additive inverse means A plus A inverse, that should be equal to 0. Multiplicative inverse means A into A inverse mod 7, that should be equivalent to 1. So here 0 contains additive inverse 0, 1 6, 2 means 2 plus 5 7 mod 7 0, 3 plus 4, then the values are reversed here. So this is the additive inverse. For 0 there is no multiplicative inverse. If you take 1, 1 into 1, 1. For 2, 2 4s are 8, 8 mod 7 is 1. For 3, 3 into 5, 15, 15 mod 7 is 1. So for the multiplicative inverse, values are retrieved. So if you check the values, these values are also the set of values which is available in Z7 series. So in this way, we can able to prove the GF of 7 with the basic arithmetic operations and its inverse. So this is an overview of three algebraic structures which are all namely group, ring, field. And the properties are closure under addition, associative under addition, additive identity, additive inverse. So if the first four properties are satisfied, it is called as group. If the commutative property is satisfied with addition, then that group is called as abelian group. If you want to prove a ring, we should take the second operator, that means multiplication operator. So we should satisfy closure, associative and distributive laws for the multiplication operation. Then it is called as ring. If you want to prove commutative ring, it should satisfy the commutativity for multiplication. And field means it should satisfy both additive inverse and also multiplicative inverse. So these are all the properties and the algebraic structures. So depending upon the question, you can able to solve these properties with the given example. So it is an overview idea of three different algebraic structures definitions with the property proofs. And the next topic is a polynomial arithmetic notation. So polynomial arithmetic expressions are denoted with a Galois field. So that means a GF of 2 or it may be 2 power n. So depending upon the powers values of x, the answer will be changed. For example, if you want to do an ordinary polynomial addition or multiplication operation, for example, f of x, some values is given, g of x value is given. If you want to do addition operation, just you add the same power values and you write the answer. For subtraction also, you do the same thing. So this is an ordinary polynomial arithmetic operation. But if you take Galois field representation, if you want to do addition, we should do XOR operation. And if you want to do multiplication of two polynomial expressions, we multiply the terms and we should remove the common terms from it. For example, so here, this is the first polynomial expression, this is the second polynomial expression. So f of x equal to x cube plus x squared. So if you want to write it in a bit form means x power 0, x power 1, x power 2, x power 3. So here x squared value is given, x power 3 value is given, but the values are not given for x power 1, x power 0. So this is the binary representation of f of x. So if I am taking g of x, the answer is x squared x plus 1. So for this one, x power 0 value is there, x power 1, x power 2 is there, x power 3 is not available. So what should you do? F of x plus g of x means just you should do XOR operation. So just to do XOR operation for this one, these are all different, 0, 1, 1. So the answer is x power 3 plus x power 1 plus x power 0. X power 0 means 1. So this is the answer. So either you write in this format, that means convert all these expressions into binary form and you do the XOR operation, then once again convert it into expression format. In this way you can able to write it. Otherwise, if any addition operation is given, just to check whether any common terms are available or not. Here f of x contains x squared common term, g of x is also contained common term x squared. We just remove those common terms from both expressions. Then only write the uncommon terms. So the uncommon terms are x cube, x plus 1. In this way, we can able to do addition operation. If you want to do multiplication operation, just you take x cube, then you multiply with this second formation. So x cube into x squared, x power 5. X cube into x, x power 4. X cube into 1, x cube. Then multiply the second term. X squared into x squared, x power 4. Plus x squared into x, x power cube. Plus x squared into 1, x squared. Then you just remove the common terms. So the uncommon terms are x power 5 plus x squared. So this is the answer for this multiplication operation. So this is a sample example, gf of 2 power n. So if the given value as n is 3, so 2 power 3 is 8. So maximum 000 to 11 values are possible. So 8 means from 0 to 7. So the answers are predicted with finite field notations. That means addition, multiplication operation, and the finding of additive inverse and multiplicative inverse for 2 power n. That means if they given it as gf of 8, you can able to write this 8 as 2 cube. Suppose if they give it as 15, so you can write it as gf of 3 into 15. That means gf of 3, gf of 5. Here 3 is a prime number, 5 is a prime number, and you do separate addition, multiplication and inverse operations for both 3 and 5. You can also combine those values for calculation of gf of 50. So in this way, we can able to do polynomial expression notations. So these are all the examples part. Exercise part, you do it by yourself. Here plus is given. You should write the answer as 2 power 8. 2 power 8 means maximum you should use 8 bits. So this is the 0th bit, first bit, second, third bit, 4, 5, 6, 7. So this is the 8-bit representation. So the answer should be written in an 8-bit format. This is also for multiplication operation. You just check the answer and you write it in 8-bit representations. So this is an overview idea of basic algebraic structures. So those structures are group, ring, fields, and the operations, basic operations are closure, associative, identity, inverse. In addition with that, commutative and distributive properties are available for proving ring and field. Thank you.